Welcome to my channel. In this video I'm going to show you a reversed polarity protection circuit with a P-channel MOSFET. But to start with a most easy reverse protection circuit with a diode. In this diagram you see a diode in the direction of the current. Let's put this on the test and I will tell you the advantage and disadvantage of using a diode as reverse protection device. Okay, let's load the diode. I'm going to measure the temperature with a thermal camera and we'll start with 100 milliamps. Like now. Oops, 100 milliamps. And the temperature is 32 degrees. .36, so it's even getting warm with 100 milliamps. Okay, stabilizes at 37.4. Let's raise the current with 100 milliamps. 200 milliamps. And it's already 50 degrees centigrade. And it stabilizes at 53. Raise it again with 100 milliamps. So we're pulling 300 milliamps now. And the temperature is going up quickly. 68. It's stabilizing. Again we raise it with 100 milliamps. And I'm at 80 degrees. And the forward voltage over the diode is 800 millivolts. .83 degrees and stabilizing, so we raise it with 100 milliamps. And half amp. .800 millivolts voltage drop. .96 degrees and stabilized, so we raise it with 100 milliamps again. .108 degrees already. .110. Okay, it stabilizes again, so we raise it with 100 milliamps, so 700 milliamps through the diode. And you see when you use this as a reversed protection circuit that you have to take care of the power it consumes, dissipates. .123 degrees, stabilized. Let's go to 800 milliamps. 133 degrees Celsius. Stabilized. 900 milliamps. Temperature is still going up and it stabilizes at 145. 1 amp. (158 degrees). As you could see in this test, the diode is getting hot even with a low current. As long as you use this in a low power device, it's perfect. But if you use a device that uses a bit more power, a P-channel MOSFET is just a better choice. To prove this, I will use a P-channel MOSFET out of my stock, an IRF9540. It's not the best choice, but it's what I have. It can handle a gate source voltage of -20 volts. I'm using the MOSFET with 13.8 volts, so I do not have to take special precautions for that. And the RDS on for this type is 0.2 ohms. And here you have the connection with the gate, the drain in the middle and the source. This is the schematic I use. The drain of the MOSFET is the input, the source is the output, and the gate is connected to the ground, and that's all there is. How does this work? When you connect the power, it will flow through the diode in the MOSFET to the source. Because the source is high now and higher than the gate, which is connected to the ground, the MOSFET starts conducting. When you reverse the power, the source is not getting a voltage and the gate is high, 13.8 volts in this case. The MOSFET does not conduct and your circuit behind the MOSFET is safe. With a multimeter I can test the diode between drain and source, but when I make the gate lower than the source, the MOSFET starts conducting in both ways. Now I make the gate high again and the MOSFET stops conducting. Let's start testing. In the left top you see the electronic load and on the right the voltage drop over the drain and source of the MOSFET. Half an amp and the MOSFET doesn't even get warm. At this point the MOSFET starts to blow itself up. You need extra cooling to prevent this from happening. Do you want to use a MOSFET where the gate source voltage is getting too high? Use the Zener diode to prevent this. Thank you for watching. Don't forget to subscribe and like. See you next time.